When we originally looked at confidence intervals, we talked about how to make an interval using the z-table, and then we discussed what happened if we didn't know that population standard deviation. In that case, we needed to use the t-table and do a t-interval. And the same things works with hypothesis testing. If we don't know that population standard deviation, then we need to resort to a t-test. In that case, our critical value is going to be x bar, the sample mean, minus mu, the population mean, divided by s over the square root of n, where s is the sample standard deviation and n is our sample size. And this is also going to require degrees of freedom. In this case, n minus 1. So we're going to start by looking at how to find the critical value. Let's suppose we have alpha equal to 0.05, degrees of freedom is 16, and a right-tailed test. We're going to need to go to our t-table. Here's our t-table. Since we want to do a one-tailed test, we're going to look down this one-tailed row at the top. We had alpha equal to 0.05, so we're going to go to the 0.05. And 16 degrees of freedom, so we go down to the 16 value. 1.746. So our critical value in this case, 1.746. Now let's suppose we have alpha equal to 0.01, 12 degrees of freedom, and a left-tailed test. I'm going to go ahead and draw the picture. We have the left side shaded. So we need to go back to our t-table. We're still in the one-tailed test, so we'll look down the one-tail row. This time we have alpha equal to 0.01 and 12 degrees of freedom. So we go down to 12 to get 2.681. However, you'll notice that that doesn't really look like the critical value since 0 is at the center. The t-table doesn't tell me when these values should be negative, so we do have to use a little common sense. Just drawing the picture, and any time your critical value is on the left, it's going to be negative. As our last example, let's let alpha equal to 0.1 with 20 degrees of freedom and a two-tailed test. Looking at our table, we're now going to look down the two-tails row since we have a two-tailed test. We're going to go to alpha equal to 0.1, and we had 20 degrees of freedom. So down to 20 to get 1.725. When I draw the picture for the two-tailed test, 1.725 corresponds to the critical value on the right. The one on the left is going to be negative 1.725. Let's now look at an example of a full test. Let's suppose that we have some investigation that claims that the average number of infections per week at a hospital in a particular state is 16.3. Looking at a particular hospital over a random sample of 10 weeks, there the mean number was 17.7 and the sample standard deviation was 1.8. We want to know if the original claim was right. Is the average actually 16.3? And we're going to test this at 0.05. So my null hypothesis, it's equal to 16.3, and we just want to know if this person is right or not. So my alternative hypothesis is that it's not equal to 16.3. I need to find the critical values. So since we have a sample size of 10, that's going to tell us that we have 9 degrees of freedom. Looking at our table, this is a two-tailed test. We said alpha was 0.05, and we had 9 degrees of freedom, so we go down to 9 to get 2.262. So we know our critical values are 2.262 and negative 2.262. The next step is to find our test value. That said, x bar, or 17.7, minus mu, 16.3, over s, 1.8, divided by the square root of n, which is 10. And we get that the test value is roughly 2.46. Looking back at this picture, 2.46 is to the right of my critical value, so it's definitely in my rejection region. So we reject H0. H0 is false. That means H1 is true. So the medical examiner in this case was wrong. The mean is actually not 16.3. Let's look at another one. Let's suppose we have a doctor that thinks that people who jog can hold more oxygen in their lungs. In order to figure that out, he looks at a random sample of 15 joggers. In that sample, their mean amount of oxygen in their lungs was 40.6 milliliters per kilogram, and the standard deviation of that sample was 6. We know on average across the entire population, the actual volume oxygen uptake is 36.7, and we want to test this at alpha equal to 0.05. So the question is it 36.7, or for joggers, is it greater than? We actually want to know if the joggers are increasing. So that's our H1. We need to find our critical value. Since we had a sample size of 15, our degrees of freedom will be 14. Looking at my table, this is a one-tailed test. I said alpha was 0.05. And we have 14 degrees of freedom. So we go down to the 14 to get 1.761. So now we have our critical value. We need to know our test value. That was x bar minus mu over s divided by the square root of n. This gives us a value of 2.52, roughly. And if we look at our picture, 2.52 is definitely somewhere in the shaded region. So that tells us we reject H0. That means H1 must be true. So yes, joggers are higher. This doctor was right that joggers are higher. So this was using the traditional method, and when we did hypothesis testing with the z-test, we had a traditional method and a p-value method. Unfortunately, the p-value method for the t-test does require some technology. If you want to, I highly suggest you Google doing a hypothesis test on a calculator, and it'll show you how to do that, but we will not do it here.